We are going to discuss the paper Raising the Cost of Malicious AI-Powered Image Editing. The work was led by Hadi Salman from MIT, and the work was presented in ICML 2023. The broad outline of the presentation is as follows. We'll first introduce the idea of the paper, then we'll discuss the proposed idea in a bit more detail. We'll go over the backgrounds of diffusion models, go over the backgrounds of adversarial perturbations, then we'll see how this paper leverages adversarial perturbations for image immunization. Then we'll discuss their qualitative and quantitative results. The paper also introduces how we can use the proposed method and also include it in policy implementation. Then we'll discuss some related works, and finally we'll conclude. If we see the trajectory of the rise of generative models, it is literally exponential. In 2014, when the first GAN paper came out and previously pix-to-pix based VAE based generative methods, this was the quality of image generation. In 2018, the big GAN paper happened and image generation quality improved significantly. And today in 2023 and 2024, we have state-of-the-art diffusion models that can generate text, videos from language description that are almost realistic. But with the rise of generative models, there's a huge proliferation of deepfakes that are being made using those models. Huge misinformation campaigns can be carried out using content that is generated by such models. Privacy violations, social and psychological impact, and security threats have been posed due to these models. If we see some examples, this fake video of Pentagon being attacked caused the S&P 500 to fall recently. Fake phishing emails have been written and have been used to target innocent civilians. Now, given we already have this monster in creation, how do we protect ourselves against such generative-based image generation and editing in general? The first and foremost things that can be done by companies on their proprietary models is digital watermarking, that is embedding marks in images or videos to detect and verify their authenticity. Another big area that is very active in research is adversarial training. We include adversarial examples in the training data of these models to make them robust to such perturbations and editing. Deepfake detection algorithms use post-hoc generation is also a common way to go. More importantly, content authenticity initiatives and awareness and education of users and policy measures being taken by governments and these organizations that make the models also can go a long way in helping us to prevent such malicious content generation. Now we look at the idea proposed in this paper. The paper proposed an idea to develop an immunization method against diffusion model-based editing. So they have the original image, which without immunization can be easily edited by state-of-the-art diffusion models, and after editing it looks pretty realistic. What the paper proposes is to use the diffusion model as a black box without tampering anything on it. We rather tamper with the input images and immunize them via adversarial attacks that leads the same diffusion model to generate unrealistic edits. For example, here after immunization, the image generated clearly looks unrealistic. Now the key tool that has been used by this paper to devise this method is to use adversarial perturbations on the inputs to latent diffusion models. The paper is general enough for this method to be considered on any set of diffusion models, but the examples and the experiments that have been shown are only on latent diffusion models as they are easier to work with and the most common category of diffusion models being used popularly by people. We'll briefly go over the background of diffusion models now. So what is generative modeling? The goal of generative modeling and deep generative modeling is to use neural networks to learn the underlying unknown training data distribution from a finite number of samples that are there in the training data set. And once we learn the training distribution, we can sample from the learned distribution to generate new data. Ignoring the details of the maths here, we see that the objective for VAE is to maximize the lower bound on log likelihood, and GANs are trying to minimize something called the Jensen-Shannon divergence, which is just one way of quantifying how close two distributions are to each other. So far, we had both VAs and GANs that follow this paradigm of sampling some latent noise vector and passing it through a model to get us some generated samples. Diffusion models are similar in some aspect, yet different. They too start from noisy object, but instead of sampling some noise vector in the latent space, they start off with some noisy sample directly in the sample space and iteratively convert it into generated samples. And we'll look into the details of this in the next slides. There are many classes of generative models. Previously, autoregressive models like Pixel CNN were famous, then VAs and GANs came over, and now denoising diffusion models are currently the state of the art. This is the forward process of diffusion models. Given we have an initial image x0, if we gradually add small amounts of Gaussian noise as t tends to infinity, we are guaranteed to tend towards an isotropic pure Gaussian noise. So the forward process basically consists of adding to the previous image step some more noise sample, and as t gets larger, this intensity of noise keeps getting bigger and bigger, and the contribution of previous time steps image keeps getting smaller and smaller. Beta t is called noise schedule. Basically, it is a hyperparameter describing how much noise is being added at each time step. The update above can equivalent be written as a sampling process from a Gaussian distribution, which is basically centered around the previous time steps image sample scaled down by 1 minus beta t, and having a variance of beta t into the identity matrix. Now the point is, can we go in the reverse direction? So can we go from xt to xt minus 1? If we can do this, this allows us to denoise and get back to the original image. But finding this exact distribution of q of xt minus 1 given xt is hard, because once we break this down using Bayes' rule, calculating xt here is intractable. So can we somehow approximate this process? So the goal of diffusion model is to learn the reverse denoising process to iteratively undo the forward process. In this way, the reverse process appears as if it is generating new data from random noise. Now, suppose we have some noisy distribution at time step t minus 1. This distribution is unknown to us in practice, and for example, it looks as follows: q of xt minus 1 and xt is here. Now, if we update from xt minus 1 to xt during the forward process is large, then we are very much uncertain about where xt minus 1 could have been. However, if the update from xt minus 1 to xt is relatively small, then we can reasonably approximate the posterior distribution as a Gaussian distribution, and we are sampling small amounts of noise from this Gaussian distribution and adding it to get from xt minus 1 to xt. In practice, we choose our noise schedule such that the forward process steps are very small. This lets us approximate the reverse posterior distribution as a Gaussian, whose parameters, the mean and the variance, can be learned via a neural net. So this and this is learned by, basically, can be learned by the diffusion model. Now, how do we train it? So if you remember, the VA also tried to do something similar, but they maximized the lower bound on the likelihood instead of the actual likelihood, since it was computationally intractable. We can apply the same trick here as well. So our loss function basically becomes log of p theta of x naught. Now if we recall the forward process, this was a forward process. Our previous time steps image scaled down by this factor, and our gradually increasing noise component. Now skipping derivations here, we can show that the final loss function that we showed there equates to this if we put xt into the previous slide's equation, where alpha t is this and alpha t bar is basically multiplication of all the previous alpha t's. Now this is our estimate of xt minus 1, which is also scaled by that beta root over of this factor, and this is basically the mean predicted by our neural network. Now instead of actually estimating the previous time set directly, what turns out to be more stable and easier to do is to rather predict the noise, and then we subtract the noise from xt to get xt minus 1. So basically our loss function finally turns out to be this, which is the actual noise minus the predicted noise, and the predicted noise is xt can again be replaced by the initial time step x0 plus all of this, because the entirety of noise being added is Gaussian, and multiple steps of Gaussian noise being added can be cumulatively seen as a drawing from a different Gaussian with different variance and all of those at time step t. So this is the training pipeline. We have this. We take basically a gradient over this, and we change the parameters of the model until and unless we converge. During sampling, we basically draw xt to be a pure Gaussian noise, and then we subtract the predicted noise at each time step from xt to get xt minus 1 until we basically reach x0, which is the fully denoised clean image. So if we see the visualization of the forward and the backward process, the forward process is basically converting the pure image into pure noise. This is a forward process of a stochastic differential equation, and Anderson in 1982 gave a tractable analytical solution of the backward process of this of the stochastic differential equation, which gives us the exact path for retrieving back the clean image, sampling basically from pure noise and starting from pure noise and subtracting small amounts of noise to get to the original denoised image. Now the unit is commonly used in diffusion models for the noising and denoising purpose. We move on to latent diffusion models and why is it needed. So training models in pixel space is extremely computationally expensive, and sampling, since it happens step by step, it cannot be parallelized. So training and sampling from diffusion models is a very computationally intensive thing and can easily take up multiple GPU days. So image synthesis at inference time is slow compared to GANs because of the iterative nature of diffusion process. Images are high dimensional, so high dimensionality is hard to deal with. So researchers observe that most bits of an image contribute only to its perceptual characteristics, like how the image looks, compared to the semantic and the conceptual composition. So in layman's terms, more are bits for describing pixel level details, while less bits are sufficient for describing the meaning of an image. So generative models should ideally focus on the latter mode. So we can separate the two components. That is what the stable diffusion paper did first. So we basically take a frozen encoder and convert images from pixel space to the latent space, and then we do the exact same diffusion process on the latent space instead of the pixel space. And after we get the decoded latent, after we get the denoised latent, sorry, we decode it to get back the generated image in pixel space. The unit style architecture remains same as it is, with cross retention and extra conditioning. It can be like textual description, masks, images, other things. So rather than applying the diffusion process directly on high dimensional full resolution input images, we compress or project the image to a smaller latent space and apply the diffusion there. So this leads to, like, most popular latent diffusion models have an autoencoder that has a reduction factor of 8. So we have a 64x smaller latent and thus save 64x in memory. So if you see the examples, these were after in the latent space. These are the initial noise versions, unlike pure noise. These are like noises of the latents, and then they are denoised to proper images. And most of the famous diffusion models that are caught the imagination of the public, like DALI 2 and Imagen, they are all latent diffusion based models. Now we look into a short background of adversarial perturbations. So adversarial examples are imperceptible perturbation that are added to the input data, in this case images, that cause a machine learning model to make incorrect predictions, classifications, or generations in this case. The objective is to understand and generate adversarial examples to test the robustness of machine learning models and to devise methods to defend against such attacks. So there are two types of adversarial attacks. One is a white box attack, where the attacker has complete knowledge of the generative model or the classification prediction model, including its artificial parameters, gradients, and things of that sort. And then we have a black box attack, where there is no knowledge of the model and can only query it to observe outputs. This work focuses more on the black box approach with only access to gradients. So the first and the most commonly used adversarial attack technique is FGSM. We won't go over the details of FGSM because the paper uses the next method. Another more robust version is projected gradient descent. So this is an iterative version of FGSM. FGSM did the adversarial attack in a one-step manner. Rather, PGD applies multiple small steps of perturbations and projects the resulting example back onto a epsilon ball around the origin input. So projected gradient descent is an iterative method used to generate adversarial examples by applying multiple small perturbations to an input image. So the objective is to find a perturbation that maximizes the model's loss function while ensuring the perturbations remain within a within a specified limit. In case of images, it is that the perturbed image should not look very different from the original image. So we start from the original image. Now at each time step, we take the gradient of the loss function, and given a small step size increment along the sign of the gradient of the loss function, we add that much change to the previous step of the image, and then if it goes outside the projected epsilon ball, we project it back to that surface where it is within x plus epsilon, and we keep doing this iteratively till convergence or till a certain number of steps have been reached. So the computing gradient part includes basically taking the gradient of the loss function with respect to the input image. So and one important thing to remember here is we are not changing parameters of the model here. We are changing the input image directly. So gradients and everything are with respect to the input image. And loss function used can be of different things depending on the use case. So here it is basically either difference in the latents or different in the original images, pixel differences. So adjust the image by moving in the direction of the gradient, and projection ensure that the projection stays within the allowable limit by projecting the perturbed image back onto the epsilon ball. So the advantage is we can use different types of norms for calculating this distance, L2 norm, L infinity norm. The paper uses L infinity norm, and L infinity norm is basically the Cheryshev norm, which basically takes the maximum of an element in a vectorized version of the input image and calculates the difference only in those. So that basically ensures that even the maximum difference in pixels are within that epsilon bar. So it is a more powerful than single step methods like FGSM. So projected gradient descent generates adversarial examples that are more challenging to detect and defend against compared to simpler methods. Now finally we move into looking into how this paper used projected gradient descent to generate adversarial perturbations and use it for image minimization. So we had seen this pipeline before as well. So the prompt was men ballroom dancing. This was the original image, and it had to be edited into this. So the adversary could use a off-the-shelf diffusion model. In this paper, they have mostly looked into the stable diffusion, latent diffusion model, and this is a generated image, and look, it looks pretty good. But if we immunize the image first by inputting some adversarial perturbations into the image, after immunization, as you can see, the image looks imperceptible. There hardly is any difference, but there are adversarial perturbations in the image, which causes the diffusion model to generate images that look clearly unrealistic and tampered. So the adversary seeks to modify an image found online. The adversary describes a textual prompt that describes the desired change, and then uses a diffusion model to generate a realistic image that matches the prompt. By immunizing the original image before the adversary can access it, we disrupt the ability to successfully perform such edits. Now here the authors use a black box adversarial attack approach, and there is no involvement of the generative latent diffusion model's parameters being changed or anything. The proposed method only adds adversarial perturbations to the input image in such a way that the generated image is visibly morphed and unrealistic, thereby easily identifiable as malicious. The authors have described two kinds of adversarial perturbations. One is the encoder attack and one is the diffusion attack. So the first approach is the encoder attack, which is a bit weaker version but still works. So we have the diffusion model as it is, and this without immunization creates the edits as required. Then we have a target image, which basically is a gray image that has to be generated if the adversarial attack has been done on the image. We don't want the model to generate successful edits, we just want it to generate gray image, as you saw in the example before. So this is basically, and we pass this into our encoder and we get the latents of this pure gray image. Now our objective is basically to minimize the difference between these two while editing this image via projected gradient descent. As we saw, so delta encoder is the changes in this image that we are doing. Delta encoder has to be within some epsilon ball, and the loss function in our case is basically the x plus delta's difference and the z target's difference. So z target in our case is this pure gray image, and pure gray image is latents, and epsilon x plus delta is the latent of the generated perturbed image. So after the delta encoder has been injected in the image, we can see that the generated image by the frozen diffusion model is unrealistic. So the encoder, as I described before, the steps are written here. The encoder attack targets the initial encoding step in the latent diffusion process, keeping the rest of the things as it is. It forces the image encoder to map the input images to a misleading latent representation, thereby disrupting the image generation process. To make the encoder produce, the objective is to make the encoder produce a latent representation that results in unrealistic and irrelevant images when passed through the diffusion model. So if we see the method, a small perceptible perturbation delta is added to the input image. The optimization problem is basically to minimize delta encoder constrained to this delta encoder mod of delta infinity being in this epsilon ball, and we minimize the difference between the latent of the perturbed image and the latent of the target, which in our case is a gray image. So we use projected gradient descent to solve this optimization problem iteratively and to find the optimal delta encoder. So we initialize delta encoder to 0, iteratively update delta to minimize the distance between the encoded perturbed image E of x plus delta and the target representation, the z target. Z target can be any other thing we choose, but here in this case we choose it to be a gray image. So the outcome is the perturbed image x plus delta encoder final after the optimization appears normal to human observers but leads to unrealistic or irrelevant generated images when passed through the latent diffusion model. So this is an example, another example. So the prompt is two men attending a wedding. Without the immunization process, you see that the generated image is pretty realistic. But with immunization, as you can see, the rest of the image is filled with gray pixels. Another common example where this method fails is here. The generated image wants two men on a plane from this original image. So this is the generated image. But even with immunization, the generated image seems pretty realistic. So this is a failure case of the weaker encoder attack. Now moving to a stronger diffusion based attack where the authors use the entire pipeline of the generation process of the latent diffusion model. So now this time, instead of just the loss function being the difference between the latent of the target image, which is gray, and the latent of the perturbed image, here the model's loss function is basically the difference between the finally generated X target and the generated X hat. So the only change is here X target is the entirety of the gray image, not Z target, and f of X plus delta is the final image generated by the perturbed image after being passed through the entire diffusion model. And as you can see, this attack is stronger and leads to generation that has gray examples. So it is worth noting that this approach, although stronger, is harder to execute. To solve the optimization problem using projected gradient descent, we need to like do backpropagation through the full diffusion model, which like and the diffusion model does repeated denoising iteratively. So this causes memory issues even on large like GPUs available to the authors. The authors are one A140 GB memory equivalent of GPU. So to address this challenge, they backpropagated not through all the steps of the diffusion process, instead only a few steps of the diffusion process, while achieving like adversarial perturbation that was still effective. Given somebody has bigger and better compute, we can simply like do the process for the entire 100 time steps of denoising. Now in the failure case of the encoder attack, if we see how diffusion attack does, here the diffusion attack does better and the generated examples look relatively more unrealistic. So this is a summary of the encoder attack that I had described before, and this is a summary of the diffusion attack that I had summarized before. Now if you go into the results, so the base latent diffusion model being used in this paper is stable diffusion version 1.5 from Hugging Face. The hyperparameters used during inference of the latent diffusion model is this is the image and height and width of the input. The guidance scale is 7.5, number of inference steps is 100, and ETA is 1. And for the adversarial attack, norm being used is the Cheryshev norm. Epsilon being used is 16 by 225. Step size, like how much each time the gradient from the loss function has to be multiplied with, that is being taken to be 2 by 225. The number of steps is 200. All of these are standard PGD adversarial attack hyperparameters that have been previously commonly used in other papers as well. So qualitative results show that immunizing against generative image variants, the authors first assess whether they can disrupt the stable diffusion model's ability to generate realistic variations of an image based on a textual prompt. And this has been a success. Visually looking, we can see that if the prompt is black cow on a beach, this was a source image, this was a generated image without adversarial perturbation, looks pretty realistic. Whereas with immunization, this looks relatively unrealistic. Like there's no beach, the cow seems to be deep in water. Now again, brown cat playing poker. The brown cat now has a football here. Here, the generated image seems relatively unrealistic. Now, if you see other examples of image editing, where other than just the text prompt, masks are also passed in, similar results come in. So this was the editable region. So their faces remain as it is, but then the rest of the image gets tampered with and we get gray images. Another example is a man sitting in a metro. So encoder attack kind of tampers with the image. Diffusion attack also does it. Seems relatively better. Without imitation, the image looks pretty realistic and looks like the man is sitting in a metro. Now, if you look into quantitative results, the authors use different uh, image similarity metrics to see how much the image is changed from being generated without adversarial attack and images being generated with adversarial attack. Common metrics used were FID, which is the fresher insufficient distance, the most common metric for evaluating generative models, precision recall, structural similarity index, and other things of this sort. So the authors used random noise as a non-trivial baseline to compare with encoder attack and diffusion attack. So if you can see, encoder attack has better scores and diffusion attack has even better scores than pure random noise being added as adversaries. And all of these things have been done over 60 images, and the variance is shown are over errors over 60 images. Another interesting way to measure this difference in generated images after adversarial attack is to measure the image prompt similarity results. So the authors measure the similarity between the edit images and the textual prompt used to guide this edit with and without immunization. Here also, they generated 60 different edits of a variety of images using different prompts and then computed the metrics. The metric used was basically cosine similarity between the clip emittance of the image and the text prompts. So if you can see without immunization, high similarity, indicating that the model effectively guides the edit as described with the textual prompt. With immunization via encoder attack, the results decreased a bit, and with diffusion attack, the results decrease even further. The conclusion is that the immunization indeed decreases the similarity between generated images and the textual prompt, thereby disrupting the model's ability to follow the prompts of the edits accurately. Now, finally, we go into the discussion and weaknesses of the method and probable policy implementations. So, is this method complete and foolproof? Absolutely no, not. We already saw in examples before that even after attacks, generated images sometimes look pretty realistic. This is a proof of a concept, and a key aspect that needs to be addressed is robustness to tampering. This is a long-standing problem to adversarial attacks. Like attack images can be taken screenshots of and passed into models where they perform perfectly well. More importantly, like can we ensure that all such popular image editing and diffusion model builders will use such methods as a step before passing in the input, and moreover, like we can always like nobody's stopping malicious actors from using Photoshop to change the image. So the entire point of this paper was to show that by increasing the friction as much as possible, we slow down the usage of such models for malicious purpose. A more foolproof approach will be to like basically integrate these methods into policy and like broader product deployment. So the fundamental challenges, as I described before, are robustness to transformation. Adversarial perturbations have become ineffective, may become ineffective after image transformations, and noise purification techniques can be applied to remove adversarial noise that has been added. So the solution is to develop robust adversarial perturbations which withstand various transformations and noise manipulations, and lots of work have been done previously and are also being done on these allied lines. Another big problem is forward compatibility. This method has been shown to work on Stable Diffusion version 1.5, but there is no guarantee that this current way of perturbing the image might be effective in future models. So the solution is to leverage transferability of adversarial examples and ensure future models account for this perturbations. And this can be ideally accomplished by planting when training such future models the current immunization adversarial perturbations as. So in my opinion, the better and more realistic way of handling these things is to use technical methods of these sort in collaboration with policymakers and developers of these models, companies who develop these models. So we can encourage or mandate cooperation from organizations developing diffusion models to provide APIs for image immunization at large scale. API should guarantee forward compatibility by including current adversarial perturbations in the training process of the future models. Also, data hosting and dissemination platforms should integrate immunization mechanisms to the platform to protect user uploaded images. Platform should support users to apply immunization effectively. Like here, we assume that we are immunizing each and every image, but then not all prompts are bad or malicious. So there should be another model which basically detects whether the applied prompt is malicious or not, and then apply the immunization process. So entire pipelines have to be made, and this process of immunization will be one part of a big pipe in the big pipeline of the entire solution. We need to align incentives between developers and users, data platforms to basically ensure widespread adaptation of these techniques at scale. Also, developers can include backdoors in their models that recognize and respect immunized images. And so fundamentally, a combined technical and policy approach is essential for effectively mitigating the risk of malicious AR image editing. This is basically a chicken and egg problem. Like malicious actors and these models will keep getting better. They will find new ways to avoid adversarial perturbations that can stop image editing, and then researchers on these sites will come up with better methods to attack and prevent images being edited in a malicious way. So by ensuring robustness, forward compatibility, and collaboration among the stakeholders, we can hope to raise the cost and the friction of generating malicious image content, thereby protecting users and their data as much as possible. Data misuse in model training has been widely studied, so where proprietary data or data that should not have been used to train these big models. So post hoc defect detection is another popular area of research, where after data has been generated, we have to identify whether it is fake or it is authentically generated. And then methods to create data that models cannot learn from, protecting against unauthorized data exploitation, have also been studied. They includes adversarial perturbations and techniques of that sort. And there are other complementary techniques like combining adversarial perturbations with defect detection and watermarking to ensure security of these models end to end. Finally, I'll conclude the presentation. So the final takeaways are AI-based malicious image manipulation is like a very serious threat, and we already see the effects of these things in media and even in our personal lives. The paper's goal is to make this process as hard as possible for malicious actors at scale. The authors utilize adversarial perturbations to do so without perturbing the diffusion model itself. This is not a foolproof method, but it increases the friction certainly. And there is a lot of research that has to be done in this direction to make things even better and even more robust. The lead author of the paper has done a live demonstration of the method being applied in this YouTube link. You can check it out after the class. Thank you for listening to my presentation. This ends my presentation.